So, hello everyone. My name is Sam Yi. I'm with Lite Technology as Associate VP of Technical Sales and Marketing. Today's presentation is going to talk about battery backup unit, or we call it BBU. So we hear a lot about integration, modular, building block. All these are nice words, very good ideas, and each has its own advantage. But for any particular application, if we look at the total cost of ownership, one approach may be better than the other. And this presentation will discuss different aspects of a BBU design within a system. Here's agenda. First of all, I'd like to take the opportunity to quickly introduce Lite Technology Corporation and its product offering and the position in industry. Then we'll talk about a BBU design, evolvement, and what Lite has been offering in this area. Then next, we will spend most of our time on Lite proposed OCPVS20 BBU module and shelf. Finally, I'd like to share with you some takeaways. Lite Technology Corporation is headquartered in Taiwan with global operations. Our manufacturing, logistics, and customer base are across all continents. Many of our products are actually among top 3 of market share in their segment. We are also the OCP Silver member and have a number of OCP-related business, such as power supply, power shelf, rack, networking switching, and many others. Before we discuss BBU, let's take a look at the technology and market drivers for power supply or power solution used in enterprise and a data center. If you look at the left, first metrics is efficiency, which is really the key driving force on technology across the board from component, module, and system. For instance, power supply efficiency today, the mainstream is 94% platinum level and is moving toward titanium as required by regulatory by year of 2023. Actually, today some PSUs even reaching 98% for AC-DC power conversion, which is really remarkable. And it's unthinkable when 80+ initiative started about 15 years ago. On the top, density is another key consideration with more and more power demand in the same or even smaller space in system. So these two metrics are essentially at the module level, and they are quickly reaching physical limits. So what do? We must have system architectural change in order to address physical limitations at the module level. So to the right, here shows one trend that when rack density is increasing, traditional embedded redundant power supply will have to move out of server chassis and use shelf solution. Here I define as a cloud 1.0. Now when density keeps increasing, 12-volt shelf will not be able to handle thousands of current. So 48-volt bus came into play, and I called it Cloud 2.0. If the rack density trend keeps going up, we can expect Cloud 3.0, which may have to use liquid cooling and other new technologies to keep up with the density demand. Architecture change also include those variations such as ATS, N+1 or N+N, 277 VAC versus 240 VAC, or even 380 high voltage DC. So there are a lot of options and variations in architecture today, but it all boils down to cost, total cost of ownership, and these considerations including PSU dollar per watt, system PUE, which is power usage, effectiveness, CapEx, OpEx, related to serviceability, interoperability, and expandability. So all these system level considerations are the key driving force for the introduction of BBU and its design optimization. That's what we are going to focus on next. We all know traditional backup system use AC UPS with lead-acid battery. They are costly, bulky, and requiring maintenance. With the lithium-ion battery technology advancing so quickly, BBU becomes a popular backup solution for enterprise server and data center. Given its performance capacity, scalability, and many other features. In early days, one design approach is to integrate the BBU module into motherboard chassis just like a power supply. It has the same form factor as PSU, so when AC is out, BBU automatically kicks in on the 1+1 configuration. It can back up other motherboard chassis when interconnected to each other. This embedded approach works beautifully, except that its capacity is still very limited due to space constraint. This is another integrated design approach, well known as Microsoft Project Olympus, which has already displayed in the past 2 OCP summits. The BBU is embedded within power supply that has 3-phase input with transfer switch also integrated. Comparing a shelf approach, this design is more scalable, providing a lot of flexibility when configuring different motherboard chassis and computing power. As we discussed earlier, when rack power density increases, embedded power is also evolving into power shelf solution. As a result, the BBU is also evolving to shelf design. This is one example. PSU is 1U height, BBU is 2U, because typically BBU shelf requires more space in order to match the power required. Here, charger-discharge circuits are integrated within power supply. So BBU is a simple battery pack with BMS control board only. The major advantage of this design is BBU thermal performance, because it does not have major heat dissipating power converter within its chassis. Of course, the PSU shelf is on top of the BBU shelf, but very limited thermal impact because they are not in the same chassis. So with this design, however, BBU cannot operate standalone because of no charger-discharger built in its own chassis. So as we move on with more understanding of BBU capabilities as well as data center needs, the BBU design approach continues to evolve. This is a conceptual design of ORV3 BBU proposed by Lite. As you will hear more during the summit, ORV3 is adopting 48-volt bus. The shelf can be 5+1 or 6+6 with 15 kilowatt or 18 kilowatt respectively. One major consideration for ORV3 BBU is that it should be a standalone backup system, like an independent source. And physically, the BBU shelf even doesn't have to be next to each other with power shelf, unlike a previous design. And this will enable BBU shelf to be truly modular building block in the rack, no matter the rack requires N+1 or N+N. It could also support a different backup time versus power. So for BBU module design, we proposed a couple of options. The first option is the 1U BBU module, and this part is battery pack with BMS control board, and this is charger module with fan in between, and it is designed for 3 to 5 minutes at full power. We also plan to support a 19-inch and a 21-inch rack, as well as reconfigurable for both N+1 and N+N shelves. Mechanically, design will also allow for replaceable battery pack for easy assembly and service. And this is another design proposal, is 2U height. Battery pack and the D2D module are detachable mechanically, there's a latch here. The battery pack can be pulled out when latch is pushed, and this will further ease the assembly. The modularity also allows for interoperability when required. As we know, in many cases, interoperability is a very desired feature. So this is what a BBU shelf looks like. One is with 1U BBU module, and the other with a 2U module. And the overall BBS is 2U height. And this is pretty much a standalone DC UPS for use in ORV3 rack. In previous design, if charger-discharger are integrated within PSU, then BBU module will have a lot of power and signal interconnection with the PSU, making it less modular. Now, with our proposed ORV3 design, this slide shows how BBS is connected within a rack, and it only connects to 48-volt bus. The communication port is for external access to its control and monitoring. Because of its standalone DC UPS feature, it provides more functionalities when needed. One is called peak load shaving. With this feature, the PSU can be optimized to lower power rating to handle base load only, while BBU handles peak load. And in most cases, peak load happens only very, very occasionally. This, however, one could argue that BBU life could be impacted because of a constantly supporting peak shaving. Of course, all trade-offs must be considered at the system level and really depend on use cases and load profile. Here's just, I want to share with you another Lite modular BBU and a BBS. Each BBU is 1.75 kilowatt with charger-discharger and current sharing capability built in. It can be configured as a 7 kilowatt BBS, or we call it DC UPS. So for more information about a similar Lite product and solutions, you are very welcome to visit our website. There are a lot of good stuff there. Currently, we have a BBS product operating in the field. This is the first rack-level BBS in China. The system consists of 4 1.1 kilowatt BBU in 1U chassis, providing 15-minute backup power time. And the built-in current sharing allows user to stack up to 4U of BBS to provide 17 kilowatt backup power. Pretty awesome. So with all this design approach and applications we have seen, lastly, my takeaway here is, in order to fully utilize BBU benefits, modular building block, open interface, and open architecture, will really open more opportunities in the future for BBU and BBS applications. Eventually, I hope BBU will be just like a standard battery cells that can be stacked, parallel, or configured to meet a variety of application needs. I believe this is also the objective of Open Rack V3. After all, once ORV3 framework is defined, it should be easy for adopters to configure their applications with minimum customizations. And that concludes my talk, and thank you for your attention.